Good morning, everyone. I hope that everybody's doing great today and that you had a wonderful weekend. We are moving forward today and looking at lesson 30.17, which deals with something called the Millikan oil drop experiment. This is on page 9 of your current lesson handout. Once Thomson had discovered the electron, which we just finished learning about in the last lesson, Robert Millikan came up with an idea that would allow him to determine the charge of the electron. And I think it's a little important here that you understand Millikan's experiment doesn't determine the charge of the electron directly. What Millikan's experiment involves is finding the charge on a very, very large number of objects, and then from those charges determining what the charge of the electron should be. The experiment is called Millikan's oil drop experiment. Of course, we now know that the charge of an electron, which we call the elementary charge, has a charge of 1.60 multiplied by 10 to the negative 19 coulombs. And we call it the elementary charge because it's the smallest unit of charge. You've learned from the time that we talked about the elementary charge that objects are allowed to have charges as long as those charges are multiples of the elementary charge or of the charge of an electron. The reason for this is that if you have an object that is charged positive, it's charged positive because a certain number of electrons have been removed from the object. And if you have an object which is charged negative, it has that negative charge because a certain number of electrons have been added to that object. And electrons are indivisible. So you can only add or subtract 1 or 2 or 3 or 117 electrons from an object, but you cannot add or subtract part of an electron. The reason these are allowable charges is because all of these charges that you're looking at right now happen to be multiples of the elementary charge. That first charge is 1 elementary charge, 2 elementary charges, 3 elementary charges, 4 elementary charges, 10 elementary charges. But we've learned that you cannot have charges on objects that are not multiples of the elementary charge. For example, 1.3 multiplied by 10 to the negative 19 coulombs is not allowed because that corresponds to part of an electron. That corresponds to 0.81 electrons being removed or added to the object. You cannot have a charge of 2.5 multiplied by 10 to the negative 19 coulombs because that happens to be 1.56 elementary charges. And I'm not going to go through all of these, but the point is that the charge of an object must be what we refer to as an integral number of elementary charges. So in Millikan's oil drop experiment, what Millikan does is devises a way to determine the charge on a very, very tiny microscopic droplet of oil, and he records that charge. Then he repeats the experiment with a different droplet of oil, and he repeats it and repeats it and repeats it. And he collects data for hundreds and thousands of different drops of oil. And what he ends up discovering is every time he gets a charge on a drop of oil, that charge that he gets is always a multiple of 1.60 multiplied by 10 to the negative 19 coulombs. This is how the charge of an electron was first determined. So what does he do? He sprays little tiny microscopic droplets of oil in between two oppositely charged parallel plates. And then what he does is he adjusts the potential difference between the plates, the voltage between the plates, until he's able to look at one particular drop that is suspended against gravity by the electric force. And we'll look at the analysis and what he does with that information in a second. But I would like to show you the apparatus. This is kind of a bare bones schematic of the apparatus. There are the two plates. They are connected to a variable potential difference. You've got an oil source where you spray a fine mist of oil above the top plate. And I don't know if you'll be able to see it in the video, but there's a tiny hole in the top of the top plate. And the drops fall through that opening. When they are falling through the opening, they are blasted with some ionizing radiation. He used X-ray radiation. All that does is it charges the drops. It either removes electrons or it causes electrons to be added to the drops. There's a little viewing microscope that you have to look through to see the drop because the drops are microscopic. You couldn't see them with the naked eye. So basically what Millikan does is he looks through there, he spies a particular drop, and then he adjusts the voltage so that he can get that drop to be suspended, which means motionless. So how was Millikan able to determine the charge on a particular oil drop? Well, he looks at the drop, and since the drop is suspended, he's already adjusted the voltage. So the drop is suspended, and since it's suspended, the two forces acting on it must be equal but opposite. We're dealing here with physics principle number 0 on your formula sheet, which says that if the forces are balanced, you have uniform motion. And by the way, stationary is the same as uniform motion. Because if the drop is stationary, it's not moving, which means its velocity is 0. And uniform motion is unchanging velocity. So this is physics principle 0. Well, how are we going to analyze this data? We're going to say that since the forces are balanced, the magnitude of the electric force and the magnitude of the gravitational force are equal. We can go to our formula sheet and see that the electric force can be found by calculating charge of the drop multiplied by the electric field, and the gravitational force can be calculated using mass of the drop times the gravitational field. This becomes charge times potential difference over distance between the plates equals mass times the gravitational field. And that's because electric field between two plates is potential difference between the plates divided by distance between the plates. So what would Millikan need to know in order for him to be able to calculate the charge of the drops? Well, he would need to know the voltage between the plates. Well, you just hook up a voltmeter and you can determine that. So the voltage is known. He would need to be able to measure the distance between the plates. Well, you take a ruler and you measure the distance between the plates. Although the drop is microscopic and you need to look through a microscope lens to see the drop, the plates themselves are not so close together that it's impossible to measure them. They might be a centimeter apart or 3 or 4 centimeters apart. He would also need to know the gravitational field strength of the Earth, which is 9.81, and then he would need to know the mass. And if we had more time, but we don't, I would get into a broader discussion of how we can determine the mass, but the mass is determined by taking the size of the drop that he sees and using the density of the oil, and with that information it's possible for him to calculate the mass. But we're not going to worry about that here. So what he does is he calculates the charge. So Millikan repeats the experiment. He calculates, based on what we just discussed, the charge of an oil drop. Then he looks at a different oil drop, and he adjusts the voltage so that that oil drop is suspended. And he calculates, based on his measurements, the charge on that oil drop. And he does this a lot. Like I said, hundreds and thousands of times. And he discovers that the charge he gets is always a multiple of 1.60 times 10 to the negative 19 coulombs, which means that's the elementary charge. This is, as I've already told you, how we originally determined the charge of the electron. Let's take a look at example 1. An oil drop is determined to have a particular mass. The mass is 3.5 multiplied by 10 to the negative 15 kilograms. When it is between two plates that are 0.95 centimeters apart, and a voltage is applied to those plates that's equal to 340 volts, then the drop is suspended. So the question is, if you had this data, what would the charge of the drop be? And then as well, how many extra electrons would there be on the drop? Well, we start off with the idea that if the drop is suspended, then there are two competing forces acting on the drop that are equal but opposite. They're equal in magnitude but opposite in direction. We can calculate the electric force using QE from our formula sheet. You should already know this, but E is not energy, it's electric field. And we can calculate the gravitational force using the formula force of gravity equals m times g. Going one step further, electric field strength is potential difference between the plates divided by distance between the plates. If you cross multiply this, you get Q times the potential difference equals m times g times d, and that gives us the charge on the drop equals m g d divided by the potential difference between the plates. Pretty easy calculation. The physics is what you're looking at on the left-hand side of the screen. That's all of the physics. Physics tells us how we can calculate the charge. The mathematics tells us what we have to do with the numbers to get our answer. mgd, that's 3.5 multiplied by 10 to the negative 15 kilograms times g is 9.81 times the distance between the plates, which is 0.95 times 10 to the negative 2 meters, and then we need to divide by the balancing voltage of 340 volts, and we get 9.6 multiplied by 10 to the negative 19 coulombs. So this is the first part of the answer to this question. The charge on the oil drop is 9.6 times 10 to the negative 19 coulombs. The other thing we're asked to determine is how many excess electrons this object has. Now, if the object has a charge of 9.6 times 10 to the negative 19 coulombs, and the charge of one electron is 1.6 times 10 to the negative 19 coulombs, most of us intuitively know you have to divide that answer by the elementary charge to get the number of electrons. If you were ever unsure though, of course you can use a ratio. One electron is 1.60 multiplied by 10 to the negative 19 coulombs. That ratio has to stay fixed, so we can write x electrons over 9.6 times 10 to the negative 19 coulombs. And when you cross multiply, you can see that you are going to have to take 9.6 times 10 to the negative 19 and divide by 1.6 times 10 to the negative 19. And you get 5.996, which would round to 6 electrons. I don't think you will ever get exactly a whole number, because all of these numbers have some rounding in them somewhere. So the number of electrons that we are dealing with here is 6. And that's the second part to this question. Of course, again, Millikan didn't know what the elementary charge was. What he did was he figured out that the elementary charge was the only number that divided an integral number of times into every single charge he measured. Now what I'd like to talk about is, what if the drop is not suspended? So there are 4 different scenarios we're going to look at here. What if the drop isn't suspended, but it's moving up or down at a constant speed? Well, if it's moving up or down at a constant speed, then it's not accelerating. And if it's not accelerating, that means the forces are still balanced. So the situation that's going on here, and you can see it in the diagram, is the exact same situation that's going on when the drop is suspended. Some people have difficulty with this physics concept. Let's imagine that the drop is moving up at 3 meters per second. That's a speed. It's moving up at a constant speed of 3 meters per second. Some people will say, well, but if it's moving up, shouldn't the force up be greater? And the answer to that question is no, because if the force up were greater, it would be moving up, but it would also be increasing its velocity up. So since it's moving at a constant velocity, those two forces are equal. So what will the analysis look like here? The analysis here will be exactly the same as the analysis was in example 1. Specifically, what you can do is say that since the forces are balanced, the magnitudes of the electric force and gravitational force must be equal. And that's your analysis. That's how you do the physics. What if the drop is accelerating up? Well, if the drop is accelerating up, then there's only one logical explanation for this. The force acting on the particle upwards must be greater than the force acting downward, which means the electric force is greater than the gravitational force. And that's why there's an acceleration. Remember, when we say acceleration is not equal to 0, that's a way of saying it accelerates. And this on your formula sheet is physics principle number 1, which I prefer to call uniform linear acceleration. When you find a net force in physics, you add the forces. But forces are vectors, so there is a very special way in which you add forces. If the forces that you're adding are in opposite directions, which they are in this situation, then you add the forces by subtracting the magnitudes. You take the magnitude of the greater force, which would be the electric force. You take that magnitude and subtract the magnitude of the lesser force, which would be the gravitational force's magnitude. So this is the force analysis that we're looking at here. You can, of course, write MA for F net, QE for electric force, and mg for gravitational force. And what I have in red would be how you would proceed to answer a physics problem in which the drop accelerated up. Now, what if it accelerates down? Well, there's two possible scenarios. If it's accelerating down with an acceleration that is more rapid than 9.81, so maybe it's accelerating down at 14 meters per second squared, or 11.6 meters per second squared. If the drop is accelerating down at a greater rate than 9.81, then the only explanation is the electric force is also acting down, and the electric force is helping the gravitational force, creating a greater acceleration. Again, we are dealing here with some accelerated motion. It is linear acceleration, which is physics principle number 1, or you can call it unbalanced forces. And what you would do is you would add the forces to get the net force. Now, how do you add two forces that are in the same direction? Well, you add the numbers together. You add the magnitudes together. So your analysis here would be that mass times acceleration would be equal to charge times electric field strength plus mass times gravitational field strength. You're adding the two magnitudes together. And if you have a situation in which this is happening, it's accelerating down at a very large number, then you would proceed by applying the physics that I have written in red. The other situation, though, is you could have the drop accelerating down at a rate that's less than 9.81. So maybe the drop is accelerating down at 4 meters per second squared, or 6 meters per second squared. And if it's accelerating down, but less than a rate of 9.81, the only explanation is there is an opposing force that's taking away some of the gravitational influence, which means that the gravitational force is down, the electric force is up, but the gravitational force is greater. And of course, we're dealing again with accelerated motion. And you would find the net force by adding the two forces together. The only thing you have to remember is when you add forces, you have rules because forces are vectors. When you add forces that are in opposite directions, you subtract the magnitudes. You take the larger force and subtract the smaller force. Of course, you go further and say m multiplied by acceleration equals m multiplied by gravitational field strength minus q multiplied by electric field strength. And again, that's what you would use to proceed in a problem where you had that kind of acceleration. All right, let's take a look at example 2. What would the acceleration of the droplet be from the previous question if we changed the voltage to 375 volts? Okay, so just to remind you, in the previous question, when we had 340 volts applied between the plates, the drop was suspended, which meant that these two forces were equal in magnitude but opposite in direction. Okay, so now we have the exact same oil drop, but we've increased the voltage to 375 volts. Well, if you increase the voltage, then you are going to get a greater electric field, and if you have a greater electric field, you're going to get a greater electric force. Now, I've exaggerated it. It's probably not going to be that much greater, but it will be greater. The gravitational force, of course, stays the same. So what analysis are we talking about with this question? What we are talking about is that the net force has a magnitude that's equal to the electric force, which is a greater amount of force up, minus the gravitational force, which is a lesser amount of force down. So we build the equation and write Ma equals QE minus mg. Go one step further and write Ma equals Q times potential difference over distance between the plates minus mg. Since we are asked to determine the acceleration, all we have to do is take that Q delta V over delta D minus mg and divide by the mass of the drop. The charge on the drop we learned in example 1 is 9.6 multiplied by 10 to the negative 19. We're going to multiply now by the new voltage of 375 volts and divide by the distance between the plates, which is still 0.95 centimeters. Then we have to subtract the force of gravity, which is the mass of the drop, 3.5 multiplied by 10 to the negative 19, 10 to the negative 15 kilograms multiplied by 9.81. This number that you're looking at right now is the net force upwards. So when we divide by the mass of 3.5 multiplied by 10 to the negative 15 kilograms, we get an acceleration upward. The answer to this question is 1.02 meters per second squared upward. It's up because we've determined the electric force up is greater. Let's take a look at B now. We're going to decrease the voltage to 300 now. Well, remember, if it was balanced at 340, then at 300, the electric force up will be smaller than it was when it was balancing the force of gravity, which means the drop is going to accelerate down. We're talking here about the drop being under the influence of the force of gravity and under the influence of the electric force, but of course the electric force is less in magnitude than the gravitational. That means the net force will have a magnitude equal to the force of gravity, its magnitude, minus the magnitude of the electric force. So what does this give us? It gives us Ma is equal to mg minus QE. You know, I didn't write the absolute value signs around G that time. The only reason I always write them around E is I don't want you to confuse this E with energy. It's not, it's electric field. Going a little bit further, we can write Ma equals mg minus Q delta V over delta D, which means our acceleration will be equal to mg minus Q delta V over delta D divided by the mass. 3.5 times 10 to the negative 15 kilograms times 9.81 minus, the charge is still the same as it was when we calculated it in example 1. It's 9.6 times 10 to the negative 19 coulombs times the voltage this time is only 300 volts. The distance between the plates is still only 0.95 centimeters. So what I've got on my calculator screen right now is the net force. If I divide that by the mass, I get 1.15 meters per second squared. So the acceleration is 1.15. The units are meters per second squared. The direction is down because we've determined that if you decrease the voltage lower than the balancing voltage, the electric force will be smaller than the balancing force, and that means that the gravitational force will be greater. What this lesson boils down to is two things. The first is that you understand Millikan determined using this method the charge on an oil drop. And then he determined the charge on a different oil drop. And he repeated this for many, many oil drops. And then he deduced, kind of like Sherlock Holmes, that the only charge that made sense for an elementary charge was 1.60 multiplied by 10 to the negative 19 coulombs, because every charge that he ever measured was always a multiple of that number. The other thing that you need to know is the physics, and the physics is really a force analysis. You either have the forces balanced or you have them unbalanced, and if they're unbalanced, you take the net force and set it equal to the sum of the forces. There are 5 problems on the next page that you can be working on for practice with Millikan's oil drop experiment. I hope that lesson made sense, and I hope you have a wonderful rest of the day. We'll talk to you guys later.